Hello guys, today we're going to talk about exponential functions. We talked a lot about these kind of functions in class, but really what do they kind of look like? If I want to graph them, what's common with them? What do they look like? We already talked about parabolas. Those are quadratic functions. Quadratic functions are those U-shaped kind of functions. We talked about linear functions. They're nothing more than just lines. There we go, linear functions. What do these exponential functions look like? Let's get started. So there are two types of exponential functions. One type of exponential functions are the ones where b, or the base, is greater than 1. All exponential functions have x, you guessed it, in the exponent. That's why they're called exponential functions, because x is in the exponent, all right? Is in exponent. So as soon as you see x in the exponent, you know it's an exponential function. The base can either be a number that's bigger than 1 or a fraction, like a number between 0 and 1, and that's on the next slide. But let's see what happens when the base is bigger than 1. Now you see how it says here bigger than 1? It doesn't say or equal to, which means that base cannot be 1, okay? Base has to be bigger than 1. If it's 1, it's not an exponential function. Well, to graph it, what I can do first is I can start off with a table of values, right? I can make x -2, -1, 0, 1, and 2. And then I can plug those x coordinates into the equation, into this x here, and figure out what the y, or f of x, is equal to, right? So if I want to find f of -2, plug in -2 for x, that really becomes 2 to the exponent -2. Based on my exponent laws, I know that that's really 1 over 2 to the exponent +2. That's how we make exponents positive, and that's really 1 over 4, so it's a quarter. And using that strategy, I can figure out all the other y's. If x is -1, 0, 1, and 2, if you could please use your calculator, use your exponent laws, and just confirm that I'm correct here, that y is equal to a quarter for the first one, a half, and then 1, 2, and 4. All right. Now, one special thing about exponential functions is that if you try to divide, actually, even before I try to divide anything, I'm going to sketch it. So if I sketch these these values, so if I do, if I plot these points on the x and y grid, I should get a curve that looks like this. Okay. Now, one important part of this curve is that if I try to see, well, like down here, close to the curve is very close to the x-axis, but I can't really tell. Is it touching the x-axis? Is it? What do you think? When will it touch the x-axis? So I'm basically asking you, for what value of x in this equation here, y is equal to 2 to the exponent x, for what value of x can my y become 0? And I mean, from the graph, you can tell, well, x should be some negative number. So let me see. If I make x maybe -10, what would y be? Well, by the rule of exponents, it would really be 1 over 2 to the exponent +10, and that's really 1 over some big number, right? 2 to the exponent +10, I don't know what it is, but I know it's big. If I make x -100, I would kind of get the same pattern. I can write it as 1 over 2 to the exponent 100, and that's an even bigger number, right? So 1 over a really big number. Now, basically 1 over a really big number, that kind of is close to 0, but it's not 0. It's close to 0, but it'll never, ever, ever be 0. So what we say is that this function here, it's actually never going to be 0. I mean, if you put 1,000 here, you're just going to get closer and closer and closer to 0, but you're never going to be 0 because you'll always have 1 over some really big astronomical number, right? So that means that this function, this red function, even though it looks like it's touching the x-axis, it's not. It's actually getting very, very close to the x-axis, and we call that an asymptote. An asymptote here, horizontal asymptote, is an imaginary line that this function approaches, but it never, ever reaches. And it'll never reach it because it just won't touch the x-axis. If you guys have decimals, I suggest you graph the function y is equal to 2 to the exponent x, and just try and zoom in as much as you can and tell me if that function ever touches the x-axis. And you should be surprised if it does, because it shouldn't. Okay, so this imaginary line that my function gets close to is called an asymptote. And horizontal function, exponential functions have a horizontal asymptote. Okay, horizontal asymptote. It's an imaginary line that a function touches. All right, so that a function gets close to but doesn't touch. Okay, you do not touch a horizontal asymptote. Okay, I guess if you're thinking about Tom and Jerry, the cartoon, Tom always wanted to catch Jerry the mouse. Dang, always, but he never did. He got so close, but never got him. horizontal asymptote is kind of the same. It's Jerry if the function is Tom. So the function here is Tom, and my asymptote is Jerry, okay? Tom will get so close to Jerry, but it'll never touch him. It'll never get him, all right? So Tom and Jerry, you guys. All right, so now another thing that happens with these exponential functions is if I look at these y values, something super cool happens. If I divide each one of those y values, so that really means I'm taking a ratio. Ratio means division of any kind. So if I take a ratio of these y values, so, and if I go from the bottom to the top, of course, I love Drake. I started from the bottom. Now I'm here. I'm not going to start singing it though. But if I start from the bottom and I say 4 divided by 2, I'm really taking a ratio of 4 over 2, 2 divided by 1, 1 divided by 0.5, and then 0.5 divided by 0.25. So there we go. If I do all of those divisions or ratios, ratio is really division, I'll get the same number, 2. And this is your proof, even if I didn't have a graph. If you take a ratio of these y values and you get the same value here, same number, that is your proof that you've got an exponential function. And not just that, look at this. This common number is called a common ratio, but that 2 is really your base here, okay? That is your common ratio. That's your base. So this is pretty cool. You can, in fact, come up with your base. You can figure out what the base is just by seeing what a table of values you've got, all right? So the next question is, what would 3 to the exponent x look like? And I mean, if I do the exact same thing, if I try and figure out my table of values, I mean, I love doing a table of values, kind of. If I put in exponent -2, right? So if my x was -2, what would y be? I hope that you recognize that it's 1 over 9. If x is -1, you get y to be 1/3 and so on. And then I can also do my division, my 9 divided by 3. So I started from the bottom with my ratio of differences. And I hope that you can tell that, hey, if I divide these numbers up, I'm going to get 3. And guess what? This 3, this common ratio, is my base here. What do you think it'll look like? It'll be the exact same thing as before. We still have that horizontal asymptote. Just going to write HA just because it's both of the words are long. So we still have that horizontal asymptote because, again, just because I changed the base, I still have the same principle. No matter what number I make x, y will never be 0. All right? And then if I just try and sketch this, so if I try to put -2 and 1/9, well, where's that? -2, 1/9 is just some really tiny number. So I'm just going to put it over here. -1 and 1/3 up there, 0 and 1, 0, 1. You should notice that most or all of exponential functions have that 0, 1 as a point, 1, 3, and then 2, 9. Yikes, it's really up here somewhere. And then if I go ahead and connect my dots, I get the same kind of pattern as my other function, except here my numbers are growing faster. So this one is a bit steeper than my 2 to the exponent x. And in fact, any function 5 to the exponent x, what do you think that'll look like? And I hope that you recognize that, hey, that function is going to be below that here. It's also going to cross at 0, 1. So that's going to be a point that's consistent for all of them. And then it's going to raise up even steeper than the 3 to the x. So this is 3 to the exponent x. And over here, we've got 5 to the exponent x for y is equal to. Okay? 10 to the exponent x, you can imagine it'll grow even faster and so on and so on. Okay? Now, what happens when that base is a small number, like 1 over 2 or 1 over 5 or 7 over 8? Again, we can use a table of values. We can make x -2, plug that into the equation here, and you guys can pause the video and try and figure out, well, what happens when I make x -2, right? What happens to the y? That's really the equation, right? Y is equal to 1/2 to the exponent x. So if I plug in -2 here, again, this negative exponent can be made positive by flipping the base. So the base becomes 2 to the exponent 2. That's really 4. And I hope that you recognize that you can do the same thing for all the other numbers. And please try. But this is the table values that I get. Okay? And then if I try to sketch these guys, I would get a graph like this. So it's very similar to the other graph that we just drew, except it's going downwards. So if this was money in my bank account, I certainly don't want this to be the graph. The other graph that we saw was the graph that I'd want to have, right? But I still have that horizontal asymptote because the same principle still applies no matter what number I make x. And in this case, I would try and make x really, really big. It doesn't matter how big x is, y will never be 0, right? Y will never end up being 0. My equation is y is equal to 1 over 2 to the exponent x. If x here is positive 100, because you see over here is where x looks like it's touching the x-axis. So if I make x 1 over 2 to the exponent 100, look at what happens. Well, based on our exponent laws, this is really 1 to the exponent 100 over 2 to the exponent 100. 1 to the exponent 100 is just 1. I mean, 1 to any exponent is just 1, right? And then I have 2 to the exponent 100. Well, guess what? That's a super big number. And again, we said anything when you have 1 divided by a big number, that value is always going to get close to 0, but it'll never be 0. It'll get closer and closer to 0, but it will not be 0. Again, we got the Tom and Jerry situation here. Again, if we do a ratio of y values, again, you guys, I'm starting from the bottom. Now I'm here. Started from the bottom. Now I'm here. Wish I knew the rest of the lyrics. But I would now get 0.5 as this common ratio. And guess what 0.5 is? Well, that's the base. So there we go. And this is how you sketch it. So again, very similar pattern, very similar look with 0, 1 is still the y-intercept, except this time it's decreasing. So this function here is decreasing, whereas the other one was increasing. It was going up, right? I'm just going to introduce a very special number in mathematics is e to the exponent x. And you can tell that this is an exponential function because x is in the exponent. But what in the world is this number e? What is it? So e is a number that's really important, and you're going to get to learn a lot about e in university. I mean, I think university profs love e so much. They use it as much as they can. It's kind of like pi and square root 2, but it's different. It's pi and square root of 2 because it's irrational. That means that, that it's a number that never ends, just like that song that doesn't end. And it's different because it's not based on geometry. So square root of 2 and pi is based on circles. E is not based on geometry. It's basically exponential growth. So, I mean, you can call it Euler's number because that's really who discovered it. But it's really based on this exponential growth and rate of change and a very special type of exponential growth. I'm not going to tell you how it was determined. I'm really going to tell you that it was really discovered by a person that does taxes. That was actually, never mind, I'm not even going to tell you the story about it. It's really all about growth when you invest money and your interest that you're investing in compounds basically every second, even more frequently than every second. So you're always earning interest on an actual dollar initial investment. So that's how it was figured out. And it turned out that E is really equal to approximately 2.718. For our purposes, we really just, if you remember that it's kind of 2.7, you're good to go. So when you have e to the exponent x here, what do you think that graph is going to look like? I'm not going to spend that stuff here, but here's e to the exponent x. It really looks like y is equal to 2 to the exponent x, right? Doesn't it look like that graph? It should, because e to the exponent x is nothing more than, remember, e is a number like that's close to 2.7. So if I had 2.7 to the exponent x, well, it should look similar to 2 to the exponent x, all right? E is super important because if I draw a tangent line, a line that touches the graph only at one point, so I'm picking a point here, and I try to find a tangent line, so that's a line that follows the shape of the graph and touches the graph only at one point. So there's that tangent line. That slope, the slope of this tangent line is also e. So it's the same number as e. It's 2.7. So it's kind of like no matter what you do to e to the x graph, no matter what you find, the answer turns out to be e as well. So that makes it very practical because there's a lot of math problems that people just can't solve. But as soon as you make the number e, oh man, just things become so easy. Another thing that you can do with e is when you take an area under the curve. So if I take an area under the curve, and I'm here picking a point, x is equal to 1. So I'm making x equal to 1, okay? So if I pick a x is equal to 1, and I make a little shadow here underneath the curve here, and I try to figure out the area underneath the curve, and you would say, oh man, how would I do that? It's so hard. How would I figure out the area? It kind of looks like triangles, but they're on a slant. How am I going to figure out the area? Guess what? With e, super easy breezy, it's also e. The area is also e, so 2.17. So that's just amazing. So many applications. I mean, you'll appreciate this when you get to calculus. So just remember, e is awesome. Now, if I just show you here different functions here, so these are all growing functions. 10 to the exponent x, which is super steep, 5 to the exponent x, less steep, but really steep, 2 to the exponent x is right here, 1.2 to the exponent x, still growing, but not nearly as fast as the others. Where would e to the x be? Try and guess. Pause the video and try and guess. If you guess between 2 and 5, you're absolutely correct. It's right there. Thank you very much. That's it. Okay. Very similar to other exponential graphs, and here are some characteristics, and you have to remember this. Increasing. I mean, if my base was between 0 and 1, my graph would be decreasing, right? It would be this shape. But other graphs, if the base is greater than 1, are increasing. Y-intercept for all of these graphs, even if it was the decreasing one, y-intercept is still 0, 1, and that's awesome. All right, and all of these guys have a horizontal asymptote at y is equal to 0. All right. And that's it. I'm going to stop there. Next time in class, we are going to talk about transformations. And we're going to apply the same type of transformations, if you remember them. A, K, D, and C. And I pulled this from a previous lesson because you should know these transformations don't change. So please, please, please review these transformations, because our next lesson is really going to talk about, hey, now that I have an exponential function, how do I put recognize these transformations, and how do I transform my graph?